mock-up of the 880 Jetliner in the Convair plant at San Diego, California. And here is Bernie Simons, the senior project engineer, to tell you more about this new jet transport.
As a man so closely associated with the 880 project, I might be under suspicion of being a little prejudiced. Therefore, I welcome this opportunity to present to you this factual, unglamorized motion picture report. However, before showing you this film, I would like to introduce you to this medium-range jet transport. It is designed to be the fastest jet airliner on the market today, and to combine elegance and comfort with rugged qualities of construction and workmanship. The 880 aircraft will be one of generous dimensions and superb performance. Its 2,000 square foot wing will hold 10,770 gallons of fuel. Its 124 foot fuselage will carry 88 to 111 passengers with their baggage and ample space for cargo. The 4 General Electric CJ805-3 engines will give the airplane a cruising speed of 615 miles per hour. The 880 encompasses all of the design and manufacturing experience gained in the manufacture of the commercial Convair liners, the 240, 340, and 440, as well as the jet aircraft, the F-102, F-106, and the 4-engine B-58. Yet, as the film will show, we do not lean entirely on this experience. On the contrary, Convair Engineering has embarked on test programs of a scope unique in aircraft manufacture. To make the 880 the safest, most reliable jet aircraft in the skies, every part must be considered all-important, even the smallest. A rivet, a weld, or a bolt, like this one, for instance.
The proven methods of design, development, and testing that gave the Convair liners their high reputation bring the same standards to the 880. Before the first flight, it must be established beyond a doubt that the tiniest part will do its job perfectly, far beyond the normal demands to be made on it. From the first test to the first flight, there can be no compromise. Tests designed to give punishment no part would have to survive must show that the 880 will be a consistent blending of elements which, like this small bolt, have failed safe. This fail-safe standard will pay high dividends in aircraft service life. Costly maintenance and lost flight time can begin with a single faulty rivet. The place to prevent failure is here, in the test rig. Even the smallest weld must prove that it will perform its function well beyond possible need. The cable which will steer the 880's big double-nose wheel is stretched, twisted, and jerked thousands of times in this performance test device to be sure it will give trouble-free service. Clear pilot vision is vital at takeoff and touchdown. To give the pilots a high level of windshield vision in bad weather, a new clearing system using bleed air from the engines is being developed. The air is fed to newly designed pressure nozzles, which direct it against the glass in a fan-shaped pattern. A rain gun, or jet pump system, developing velocities up to 150 knots, simulates a 1-inch-per-hour rainfall at takeoff and touchdown speeds. Here we see a test landing. The rain strikes, and pilot vision is impaired. Runway touchdown, 15 seconds. Speed, 120 knots. The clearing system is switched on. Almost instantly, most of the windshield is cleared, and good visual contact is possible again. Another series of windshield tests is made to study the impact effect of flying birds, a potential hazard to aircraft and personnel. To eliminate this danger, extensive testing of new windshield designs is carried out to find one of sufficient impact resistance. To pass the test, the windshield must prove that it offers good protection for the pilots. The dummy and windshield are properly positioned. To closely simulate the possible damage of the impact of a real bird, a newly chloroformed chicken is fired at the test windshield by a high-pressure air gun. The air gun can fire the chicken against the test windshield with a velocity corresponding to the 880's cruising speed. Compressed air is built up in the gun. Pressure can be regulated to fire the bird at the necessary speed. Pressure setting and firing is done at a safe distance by remote control. Pressure continues to increase until firing level is reached. The glass fractures, but it does not shatter. In this test, the dummy showed no damage to his simulated human tissue. Here is the same test in slow motion from the pilot's point of view. Although in this test the windshield passed satisfactorily, Convair engineers prefer a newly developed laminated shield being tested now. In an airliner of the 880's capabilities, great structural strength is the first consideration in design. To make certain that these specifications are met, sections of the 880's fuselage are subjected to exhaustive tests. In this test stand, a 1/4 fuselage section is artificially ruptured to simulate possible in-flight damage to the skin. Compressed air is pumped into the test specimen and fluctuated with a pressure switch. It was necessary to learn if there would be a dangerous growth in the size of the crack and whether it would weaken the structure below the level of flight safety. A maximum pressure of 10 pounds per square inch was reached at one point in this test. Following each series of 50 pressure cycles, measurements are taken of the crack and compared with the length of the crack at the beginning of the test. Although the crack grew slightly, there was no indication of serious traveling of the rupture. The section depressurizes slowly without seriously weakening the structure. In another test, a 9-inch steel dagger is dropped with penetrating force into the fully pressurized fuselage section. The artificial rupture and dagger test give conclusive proof of the high level of structural strength built into the 880. Extensive fatigue testing of the forged window frames designed for the 880 have been conducted with satisfactory results. Other pressure tests conducted on the single inner window bore out that it can withstand double the normal cabin pressure. This proves that the single inner window would hold even if the double outer windows were lost. A test to measure the shear strength of the fuselage skin is set up. Increased loads are applied to the specimen until stresses far exceeding the effects of the most adverse flight or landing conditions are reached. After loads of 110,000 pounds, the fuselage lost its temporary wrinkling and recovered its normal shape and strength completely when pressure was released. Above 130,000 pounds, permanent buckling began to appear. The section withstood a total load of 180,000 pounds before failing. Test results, more than adequate. Before designs for a wing access door are accepted, comparison tests of wing sections with and without the door are made. In this test rig, the wing sections were subjected to spectrum fatigue loading, which reproduces all significant loads applied to the wing in flight. Test results showed that great structural strength could be retained in the wing with the added advantage of an access door. High margins of safety are also incorporated even into the design of the 880's tail antenna. Communications plans include a 1,000-watt transmission system for a range of 1,000 miles at 40,000 feet. A careful study of antenna impedances is made on a test model built high above possible electrical interferences. To duplicate the electrical characteristics of the 880, a model is covered with a fine metal mesh. A satisfactorily strong antenna would place the insulating gap above the highest rudder hinge. Still, the 880 must have an antenna that meets the specification for range and power. A remote control system is installed to eliminate error in readings caused by the proximity of the engineers themselves. When the test system is adjusted, the model is closed, and the engineers go below to the remote control station. Now, a system of pulleys operates the antenna system in the model. An error of even 1 ohm is too much. The readings must be exact. In this way, accurate measurements of limits and ranges are made. These tests paved the way for an antenna which will combine excellent transmission and reception quality with long range and great structural strength in the vertical stabilizer. To make an accurate check on the air conditioning system and temperature control, a completely equipped metal passenger section is delivered to the cold chamber. Here, temperatures can be varied from -100 to +200 degrees Fahrenheit to produce conditions far more extreme than any the 880 will ever encounter. The 880 mock-up room at Convair is the proving ground for experimental design and fixture testing. The consideration given here to passenger comfort is also evident in the 880's pilot compartment. Convenient features ranging in importance from this easily accessible flight kit and data case holder to a secure place to put a cup of coffee have been incorporated. The crew seats are contoured and completely adjustable to any normal operational position. Convair has pioneered in pilot-designed cockpits, and the 880's front office is designed to reduce pilot fatigue and allow the men who fly it to do their jobs in the easiest, most efficient way possible. Movable armrests make it easy to get in and out. These are the men who will be in these chairs on the maiden flight of the 880. Their combined flight time of over 25,000 hours makes them experts in matters of cockpit comfort and safety. This schematic fuel metering and routing board tells the engineer at a glance the condition of the entire fuel flow system. The position of every fuel valve and pump is clearly visible. His tilted instrument panel puts every control for the electrical, air conditioning, ignition, oil, and flight control systems at his fingertips. The panel is angled so that, if necessary, the pilot can read the instruments from his station. These specially designed fire control handles are within easy reach of both pilots. A pull on the red handle automatically stops fuel flow and ignition to the affected engine. If the trouble persists, the blinker changes to steady red, and the extinguishing switch, safety locked behind the handle, can be operated. 2 sets of levers on this cleanly designed throttle column make it impossible to activate the reverse thrust baffles on the engines without first reducing power. Another safety feature. Special designing has been undertaken to cut the ground handling and out-of-service time costs to an absolute minimum with this aircraft. As an example of the attention given to standard airline maintenance procedures, engine replacement methods for the 880 have been greatly simplified. Engine removal time has been reduced considerably. With the clamshell cowl opened clear out, work can begin on both sides of the engine at once. On engine left, 4 fluid disconnections are quickly made. At the same time, 3 power cable disconnections on engine right and 2 bleed air duct joints. This done, the engine is ready for removal. A specially designed removal cart is wheeled under the engine. Guide rails on the cart are easily lined up with corresponding points on the engine. When the cart has been centered, the cart bed is raised until it is in line with anchor points. The few bolts holding the engine to the frame are removed and rail clamps are tightened down. The engine is then lowered and the cart is ready for rapid, secure movement to the repair shop. Engine installation is the exact reversal of the removal steps. The tooling program, moving in step with the design and testing program, will be ready to shape the 880 when every single part and subassembly has been tested to the rigid, fail-safe standards. Minor components are being produced even now. By December 1957, manufacturing on the major component level will have begun. In November of 1958, the first completed production 880 will roll off the assembly line to be test flown the following January. In the meantime, more and more tests are being conducted on increasingly larger test specimens, and never losing sight of the 880's intended purpose, an aircraft of outstanding performance and economy.